Swayam Prabha. Digital India. Educated India.
Good morning, boys. So what we have here, we are going to continue the problem which we started in the last class, is where for this plate we have 4 nodes, and then we have assembled the element global stiffness matrix from the elemental matrices. So all these things had to be filled up. I think I'll leave it to you. Then we have this here. These are the global degrees of freedom, U1, V1, U2, V2, U3, V3, U4. So now we have to solve for the displacement. So the way it looks now is that we can take the K inverse and then take it to F and then we do it. But what happens here is that the rank of this K matrix is less than 8, so you cannot really invert. In fact, rank, if you find out, it turns out to be 5, which also tells us that there are 5 independent equations, or on the other hand, 8 minus 5 is equal to 3. So that gives you rigid body modes. So that means that the body can go into this kind of displacement modes without any application of the external forces. So that means that those modes need to be eliminated before we attempt to solve. So that's, in fact, that's how the minimum boundary conditions that have been prescribed here. So these are 2 are removed here and 1 removed here, which will essentially remove all the 3 rigid body modes. And if you want, you can actually apply more displacement boundary conditions, but at least these are the minimum boundary conditions. So let us now try to, we have applied this U1 is equal to 0, V1 is equal to 0, and U4 is equal to 0. So these are the 3 values which will be assigned 0. And then we had to solve for others, U2, V2, U3, V3, and V4. So 5 unknowns are there. We have 8 equations. So the question is that which 5 we can choose out of these 3 and solve for the 5 unknowns. So here, this is which need to be considered depends upon the kind of mathematical procedure we adopted in deriving this equation. In fact, if you this procedure of variation formulation, that's minimization of potential energy. So in fact, for example, the first equation here has been obtained by taking the derivative of pi with respect to u1, right? And the second one is obtained by taking the derivative of pi with respect to v1 and so on. So the last one is obtained by taking the derivative with respect to v4. Okay, so that's number 1. Number 2 is that under this principle of minimum potential energy, so there is a condition there, if you recall. So the admissible set is that set of displacements which satisfy the kinematic boundary conditions. Kinematic means here the displacement prescribed boundary conditions. So whatever you vary the displacements, nodal displacements, so you can vary only U2, V2, U3, V3 and V4 here. So this out of the potential energy, so these things can be changed, and then you find what is the minimum potential energy corresponding to which set of these displacements. Okay, and so there it implies that only these things can be U2, V2, U3, V3 and V4 can be changed. The potential energy will be minimized with respect to this, and then the displacement set will have no control on this u1, v1 and u4. So they had to be constrained as 0 as given by the displacement boundary condition. So that means that, so according to this, so you can see that your minimization with respect to u1 is not valid because u1 cannot be varied, neither v1 can be varied nor u4 can be varied. So that means that you can consider only, so the first, I'll write here, first, second and the seventh equation cannot be considered for solution purpose as they were obtained by invoking dou pi by dou u1 is equal to 0, dou pi by dou v1 equal to 0, dou pi by dou this one u4 is equal to 0, because these are given displacement boundary conditions. So they cannot be changed. They remain fixed as whatever has been given to be. And so the first, second and seventh equations cannot be considered because they were obtained by taking a variation with respect to u1, v1, u4 and so on. So that means that you should not consider the first row and the seventh row, right? And then you have to consider only the other equations. So that is third, fourth, fifth, sixth and eighth equation. So that means that, so if you have to rearrange them by taking u2, v2, u3, v3 and v4. So rearranging the equations, so this is how it looks like, and this I did not use, but I'll put it for the sake of completeness. I have something to say about that. It is 1000, 0. So these are the 5 equations which we consider. So that means that we consider this, we consider this, we consider this, we consider this, and okay, so these are the 5 equations which we considered, and we regroup them so that they look like this one. And this also, because it's 8 columns, right? So this is 5 by 5. And these things also have been there. And those things are also put. Why I put there is that these displacement boundary conditions which we have put here, now of course they are 0 here, in this problem, u1, v1, v4, sorry, u4, this is u4 are 0. So anyway, so this contribution drops down to 0. So essentially you will have this 5 by 5 matrix together with this 5 nodal forces, and then you can solve for them. Okay, so if you solve for them, so what will you get here? Solving above equation, we will get U2, V2, U3, V3 and V4 as 0.74. So if you solve this matrix, this 5 by 5 matrix, and then you invert it and then you take it to the right side and then you can get this solution. Okay. And this is together with, of course, U1, V1, U4 or 0. So this is now the displacement solution, right? So just for the sake of completeness, so if you want to retrieve stresses, say stresses, say in element 1, so if you want to find stresses in element 1, what is that which we need here? We need strain and then we pre-multiply with D to get the stresses. So to get the strains, so we need the B matrix multiplied by here. So for element 1, the B matrix consists of the degrees of freedom U1, V1, U2, V2, U3. Okay, so this is the B matrix. In fact, we can even include the U1, V1 and U2, V2 is 0.714 and V2 is 0 and U3 is 0.714, 0, 10 to the power of. Okay, so this is how you know B for the element and then this is what you get. So here the strains, when you get this, you get strains, and then after that what do you get? After that you have to pre-multiply with D. Still there's a little bit discussion here. I think I still require this a little bit. Okay, so to get stresses, so what we need is sigma x, sigma y, tau x, y in so after getting epsilon x, epsilon y, gamma x, y here, so you get that substituted here. I think I'll leave this calculation and you get it as, okay, you get the stresses as 500, 0, 0. A little bit of calculation, so you do that. Okay. On the other hand, just to go back and look for which equations we need to consider for solution, also can be looked at this way, that this one here, you can also argue it in slightly in a different manner. So what we have here is that, so your K global is there and multiplying U1, V1, U2, V2, U3, V3. So this is equal to the applied force here which is 0, 0. Yeah, so we would like to look at this one again so that we get better idea of which equations that need to be used to get the displacement solution. So one is that these are given, as we say, but apart from that, we also know in reality that these nodes at 1, for example, also have certain reactions, or 1x, or 1y, and so similarly here, or 4x. In fact, these also these are reactions. So if you want, we can also put them here. So this is R1x, R1y, and here. So these are actually the reactions. In fact, you can add them here, right? So that means that, let me write here itself. So maybe I'll write it here. Let me write it right here. So that means that the force here on node 1 also includes the reaction force. Okay, so these essentially are also unknown. So it looks like that now when we try to solve for these displacements, so you cannot use the first equation because on the right side we do not know the reactions. So first, second, and fifth equation, seventh equation cannot be used meaningfully because the right side is not known. So that way also you can say that the first, second, and seventh equation cannot be used for the solution purpose. On the other hand, we also argued it that from the minimum potential energy point of view, so the minimization or the variation can be done with respect to only these 5 displacements, not with respect to U1, V1, U4, because they are given, they are kinematically constrained values. So we cannot make a change the variation in that, and so we cannot use them. Okay. So this is, I hope you, after getting these displacements, so we have extracted the nodal displacements for element 1, and then we pre-multiplied with B to get the strains, and then we pre-multiplied with D to get the stresses. So this is how we can solve the problem completely. Okay, this is a simple problem, but I went through all the steps to illustrate all the major issues in this problem. This analysis of 2D can be extended to 3D very easily. So let's just do that, because we keep doing it 2D and 3D simultaneously, because the extension of 2D to 3D is very easy. So extending this concept to this finite element procedure to 3D solid mechanics. So how do we extend it to 3D solid mechanics now here? So here there are 3 equations here, and in fact there are 3 equations, but if you follow the variational principle, then we deal with the 3 displacements, right? And 3 displacements. And then we have 6 strain components. We have gone through this one. And 6 stresses. Okay. Okay. So now we have the same approach, and the earlier in the 2D case we have used the triangle as our element. So here we use in 3D. Okay, so this is the so these are types of boundary conditions. So here we have the 3-dimensional body. So when come to the element, so the extension of triangle in 2D to 3D will be a tetrahedron. A tetrahedron here. So this is a element is a 4-noded tetrahedron. Okay. So here so 4 nodes. So what we do here is that there are 3 degrees of freedom for each node. So for example, if you want to find out the the x displacement, now we can write it in terms of so I'll write it here. So you can see here you have 4 nodes and 4 shape functions. So this is for u. So similarly, you can also do it for y displacement. And w. Okay, so these are 3 displacements UVW, and then these are expressed in terms of nodal shape functions and nodal displacements here. Okay, so what we require here is that what is Ni? Ni we can write it as Ai plus Bix and with additional variable di. So this is the basic expression for the shape function. So how do you get this ai, bi, ci, di? So these getting, of course, earlier we did that using the property that ni will have a value of 1 at node I and will have a value of 0 at all the other nodes. So if you use that, so Ni is 1 at node I. That means that xi, yi, zi, and at other nodes. So this is the information which we have for Ni, and then we can use this information to get the AI, BI, CI. So to get Ni here, so we have 1 Xi, Yi, Zi, and here you have AI, BI. Okay, and so you can very easily see that the first equation will have 1 on the right side. So these are the 4 equations by which we should be able to find out this AI, BI, CI, DI. So these follow exactly the same procedure as 2D, except that these involve more number of equations. Okay, a little bit more complex here. So this way you have, this is the basic thing, and which is written in terms of nodal values, and then this is how we can calculate AI, BI, CI, DI. So if you want to get AJ, BJ, CJ, DJ, so this matrix remains same, but this will be having a value of 1. So that means that it's in the second row. So it will be 0, 1, 0, 0. So like this, we can actually calculate all these values. Okay. Now, what is that which we require here? If you recall, what we require is that to evaluate K of the element, we have B transpose dB over volume of the element. Okay, so what is B here? So B is, so knowing that B relates the strains, B relates strains with nodal displacement. So what does this mean? So what are the strains here? The strains are 6 components. So these are the 6 strain components, and here you have a B. So these are displacements, nodal displacements. What are that? So it is UI, VI, WI, UJ, VJ, WJ, and all the way up to WL. Okay. So this is how we'll write it. So essentially, what is epsilon x to start with? So this is in terms of nodal values, but before that, we actually have epsilon x. If you recall, epsilon x is what? Dou u by dou x. Okay. And so similarly, epsilon z, epsilon y. Okay. So if that is the case, so just extending our 2D concept, so this simply becomes AI 0, 0 or BI. So if you go back to this one, the derivative with x will be BI here. So it is BI 0, 0, BJ 0, 0, BK 0, 0, and BL. Okay, so similarly CI 0, and this is DI. So like this, so these are all functions of coordinates BI, BJ, BK, which we get from here, and so this is the B matrix. Okay, so once you have this, so it is nothing but K of the element So here when you do this integration, you can realize that B is constant. So realize that B is constant for 4-noded tetrahedron. So we have it simply B transpose dB here multiplied by the volume of the element. Okay, so the volume of the element is nothing but this one, 1/6 of this determinant. So you can also find out from your coordinate geometry. Okay, so like this, so we have the K matrix defined. So similarly, we have, just like in 2D, we also have the contribution from the body forces. Okay, so this is how we can extend our 2D concept of the 2D solid mechanics to 3D solid mechanics. Okay, so it's just 1 degree of freedom more than the two-dimensional analysis, and the rest of it just follows exactly the same steps. Okay, and I think we'll stop it here and we'll continue this one in the next class for other type of important factors such as thermostresses and other things, higher degree elements. So for the moment, we'll take a break and we'll say bye-bye.